support definitely. So any risk architecture, the rule is any risk architecture must employ pipelining mechanism. What is pipelining mechanism? Pipelining refers to what we call a mechanism in which parallel activities are taking place or concurrent activities are taking place within the same clock cycle of execution, same clock cycle of time. So in one clock cycle, execution is taking place at the same time, decode is taking place at the same time, fetch is taking place. This is for a 3-stage pipeline. Suppose if you go for a 5-stage pipeline, execution is taking place, decode is taking place, fetch is taking place, and some other things called as register write or memory write operations are also taking place. So when multiple or when concurrent activities are taking place within the same clock cycle, we call such kind of design as what we call uh, what do you say, pipeline design. So that is called as pipeline. Pipelining is a must in the case of a risk architecture. Pipelining may be used in CISC architecture, may not be used in CISC architecture, but the rule is any risk architecture must use pipelining. So because of this pipelining feature, okay, because of this pipelining feature, the CPU performance gets increased. The CPU is able to execute more number of instructions in a certain amount of time. So if I consider 1 second, it can execute lots of instructions in 1 second if it is a pipeline CPU architecture, as compared to a CPU architecture which is not pipeline. So in 1 second, the number of instructions which a non-pipeline CPU architecture will be executing will be less as compared to the number of instructions which a pipeline CPU architecture will be executing. So ARM, being a risk architecture, aims at performance. So performance is because of pipelining. Risk architectures always try to aim at performance. CISC architecture do not give much importance to performance, but rather they give importance to the operations to be performed. Okay, they give more preference or priority to the complexity of the CPU architecture and the features it supports. Whereas if you go for a risk architecture, it gives more preference to what we call performance. So risk architectures are performance-oriented architectures, whereas CISC architectures are less performance-oriented architectures. So ARM, being a risk architecture, is it's having a performance capability or performance feature. So ARM is a 32-bit processor core. 32-bit here processor core implies that it has a 32-bit address bus, it has a 32-bit data bus, it has a 32-bit instruction set. I repeat, the 32-bit processor core here implies that it has a 32-bit address bus, it has a 32-bit data bus, it has every instruction which is 32-bit in size. Okay, so apart from that, the ALU processing capacity is also 32-bit. So this is what I mean by 32-bit processor core. So the ARM architecture has been very carefully designed or very cleverly designed such that for designing the ARM architecture, it has taken less number of logic gates. So if we take ARM architecture and we take some other CPU architecture of the same processing capability, it has been what we call researched that the ARM architecture has less number of logic gates put together to realize the architecture for the same capability as compared to the other CPU architectures. So in that sense, what we mean by is ARM has a reduced gate count. That means the number of logic gates put together to design the ARM architecture is very, very less as compared to the other CPU architectures of the same processing capacity. Means if I take a 32-bit CPU ARM architecture and I take a 32-bit some other CPU architecture, maybe a RISC architecture or a CISC architecture, ARM architecture takes very less number of logic gates. So if it takes less number of logic gates, what happens is the power consumption decreases. If it takes less number of logic gates, the fan in and fan outs will decrease. If it takes less number of logic gates, then the propagation delay is also reduced. So since propagation delay is reduced, the fan-in fan-outs are reduced and power consumption is reduced. So hence the ARM architecture is suitable for small, low power, high performance based implementations. Next, the ARM architecture supports high code density. So what do we mean by high code density here is the ARM architecture supports, that is the ARM7 architecture supports two instruction sets. One instruction set is called as the ARM instruction set, which is of size 32-bit in every instruction of that set. And then the other instruction set it supports is called as 16-bit instruction set, which is called as thumb instruction set. So we have two instruction sets in ARM7 architecture, 32-bit instruction set, in which every instruction is 32-bit in size, and we have 16-bit instruction set, which is called as thumb instruction set, in which every instruction is 16-bit in size. So if I want a performance-oriented application, I will prefer to choose to write the application using 32-bit instruction set. If I want memory conservation related application, means the amount of memory that should be consumed for writing this application to be executed on ARM should not take more memory, it should take less amount of memory. So in that kind of situations, prefer to go for what we call thumb instruction set. So if I'm writing a program which consists of 100 instructions in ARM and the size is 32-bit, that is 4 bytes. So the total size of the program will be 4 into 100 instructions. That is 400 bytes will be the size of the program. Now, if the same application has been written with, let us say, 16-bit instructions, assuming that in place of 100 instructions, it is taking maybe around, say, 70 instructions. It is taking around, say, 70 instructions. Sorry, if it is taking, let's take, it is taking 120 instructions. If it is taking somewhere around 120 instructions to complete the same application using the thumb instruction set, then 120 instructions, each instruction size is 2 bytes because it's a 16-bit instructions. So 120 instructions into 2, 120 instructions into 2, that is 240 bytes. Whereas the same application, when it was written using 100 instructions, it had taken 400 bytes. So 400 bytes if written using ARM instruction set, and 240 bytes if written using thumb instruction set. So I'm just trying to give an idea that when an application is written using ARM instruction set, it takes more space. When the same application is written using thumb instruction set, probably it may take slightly more instructions than it had taken for ARM instruction set. But even though it probably takes slightly more number of instructions than it had taken for writing the same application in ARM instruction set, the overall size of the program is reduced. So even if I say that the program which was written in ARM instructions had taken 100 instructions, and the same program, if it had been written using thumb instructions, even if I say it takes 150 instructions, so 150 multiplied by 2 is 300 bytes, whereas 100 multiplied by 4 is 400 bytes. So 400 bytes is the size of the program if written using ARM instruction set. 300 bytes is the size of the program if written using thumb instruction set. So the point here is, when an application is written using thumb instruction set, then it takes less space in the memory of the ARM architecture. So that is what we mean by high code density. High code density implies that more number of instructions can be accommodated in the given space of the ARM memory. More number of instructions can be accommodated in the given space of the ARM memory if the program is written using what we call a thumb instruction set. That is called as high code density. The next feature says that the ARM architecture occupies a very small area on the silicon wafer because, as we said that previously, it has a reduced gate count. So since the reduced gate count, it has been designed using less number of logic gates. So it takes very less area on the silicon wafer. Next. Next set of features. So the ARM architecture incorporates three levels of on-chip hardware debug technology, which are as follows: JTAG, Joint Test Action Group. JTAG stands for Joint Test Action Group. So JTAG is nothing but a kind of serial communication protocol available on the ARM core, whereby users can carry out debugging operations with respect to the ARM core. What we mean by debugging operations, for example, if I want to go for single step debugging, or I want to go for debugging based on breakpoints, or I want to go for viewing the viewing the content of registers, or I want to change the content of registers, or I want to view the content of memory ROM or RAM, or change the content of the memory ROM or RAM, or I want to change the instructions of a code section. So all this type of operations can be comfortably done using what we call JTAG, Joint Test Action Group. So Joint Test Action Group refers to a serial communication protocol uh, available in the ARM core, which allows us to go for debugging with respect to the ARM core when writing applications. So that's called as the hardware debugging. Apart from JTAG, there are other levels of debugging that is called as ETM, Embedded Trace Module, ETM, and the other one is called as RTM, Real-Time Monitor. So the combination of the Embedded Trace Module with the Real-Time Monitor help an application developer to go for real-time testing on what we call the ARM architecture. Means the embedded trace module with the real-time monitor will help the application developer assess what is the performance of the ARM architecture in the real-time environment. So what is the percentage utilization of the CPU for your application? Okay, what is the time taken for the instructions, or what is the time taken for the functions or routines? What is the time taken for the overall application? Okay, so such kind of performance related metrics can be observed during debugging with the help of what we call these high-end debugging techniques called as embedded trace module and real-time monitor. So these two debugging techniques, embedded trace module and real-time monitor, are a bit higher end debugging techniques used for in ARM architecture for real-time testing. That was the briefing about the three levels of debugging technologies which is supported in the ARM architecture. Next, coming down to the next set of features, we have the ARM architecture being a RISC architecture, and usually the feature of RISC architecture is it does not contain lots of addressing modes. So ARM architecture has relatively less number of addressing modes, maybe around 4 to 5 addressing modes, or just relatively few number of addressing modes. So when we come to the programming part, you will come to know that anyway. Okay, so it has less number of addressing modes. Are you guys noting down anything as I'm writing, as I'm dictating? V19HE7M3. Are you noting down or just listening? Okay, okay, fine. So I'll go a little bit more slower. Please don't note down anything because right now, if you note down things, it will happen slowly. Whatever slides I have given, just follow the slides and listen to the explanation. Don't try to note down things right now. Okay, so once again, quickly, I will revise these points. So ARM core supports a RISC architecture. Then it's a 32-bit processor core, which implies that it supports a 32-bit address bus. It supports a 32-bit data bus. It supports a 32-bit ALU. It supports 32-bit instructions. And since it supports 32-bit address bus, that means the total amount of physical memory which the core can address is given as 2 power 32. 2 power 32 is 4 GB of physical memory. So this 4 GB of physical memory, some part of the 4 GB of physical memory can be allotted for read-only memory. Some part of the 4 GB of memory can be allotted for random access memory, RAM, and some part of the 4 GB memory can be allotted for special function registers, SFRs. So this entire 4 GB of addressable memory is allotted in that way. Then the ARM architecture is a very carefully and cleverly designed architecture which has been designed with a less number of logic gate counts. Hence, it has a reduced gate count. So the benefit of having a reduced gate count is it is small or compact in terms of design. It takes low power because of less number of logic gates and the load is minimized, and high performance because of the less number of logic gates, and fan-ins, fan-outs are reduced, propagation delays are reduced. So it is suitable for small, low power, high performance implementations. Next, ARM features high code density. So high code density implies that the ARM architecture supports two instruction sets. One instruction set is 32-bit instruction set named as ARM instruction set. The other instruction set is 16-bit instruction set named as thumb instruction set. So the thumb instruction set is 16-bit in size, that is half the size of an ARM instruction. So if an application is written using ARM instructions, let us say that application takes 100 bytes, 100 instructions. So 100 into 4 bytes per instruction. So total size of the application is 400 bytes. Okay, 100 instructions into 4 bytes, that is 400 instructions. Now, if the same application is written using thumb instructions, usually it may take slightly more number of instructions in thumb as compared to the ARM instructions. So let us say it takes around 130 or 150 instructions as compared to the 100 instructions it had taken. So if it takes around 130 or 150 instructions, so 150 instructions multiplied by 2 bytes per instruction, that gives us around 300 instructions. So the total number of memory consumed when application is written using thumb instructions is reduced as compared to the same application written using ARM instructions. That means the more number of instructions can be accommodated in a given space of the ARM core if the application is written using thumb instructions. We call this feature as high code density. And the ARM architecture takes a very small area on the silicon wafer. This was about a quick revision about this particular slide. The next slide is talking about the debugging capabilities which are supported by the ARM architecture. So ARM supports basic level of debugging, which is called as JTAG, Joint Test Action Group. So this basic level of debugging allows us as a programmer to debug an application in terms of single step debugging, in terms of breakpoint debugging, in terms of what we call observing the registers debugging, in terms of observing variables or memory locations debugging. Okay, we also have something called as injection. Injection here implies that a particular instruction in ARM at the time of debugging can be replaced with another instructions. Means if we are debugging the instruction step by step in ARM architecture and we come to a point where we realize that that instruction in this program is not appropriate, so we can replace that instruction at that point with a correct instruction at the time of debugging itself. Means I don't need to write the program again and compile or assemble the program and then load the program for again debugging from fresh. When I realize that the next instruction which I'm going to debug is probably logically not correct, I can replace that instruction with an appropriate instruction there and then itself. This type of feature is called as injection. Injection, that means I can replace a given instruction in a memory with a correct and appropriate instruction before I continue to debug the application. This feature is supported in what we call the ARM JTAG, Joint Test Action Group Support, which is actually a serial communication protocol used for debugging. So any ARM architecture definitely supports JTAG. Next, you have ETM, Embedded Trace Module, and you have real-time monitor. So the combination of these two debugging techniques helps us to observe the percentage utilization of a CPU for our application. If our application consists of several functions, how much percentage CPU is utilized when these respective functions are executing? Is it taking 10% of CPU time, or 5% of CPU time, or 1% of CPU time, or 0.5% of CPU time, or 90% of CPU time? So this percentage utilization of the CPU can be observed. Apart from the percentage utilization of the CPU, we can also observe what we call uh, things like time for execution. So how much time every statement is taking for execution, how much time every function is taking for execution. This type of performance metrics related information can be observed using ETM combined with real-time monitor. So these are the features of the hardware debugging technology incorporated in the ARM architecture. Next, the ARM architecture is a RISC architecture, and the usual feature or characteristics of RISC architecture is that they do not support many addressing modes. So ARM architecture itself, being a RISC architecture, does not support many addressing modes. What are the addressing modes? You will come to know when we start the programming related discussions. But right now it does not support many addressing modes. Next, the ARM architecture being a RISC architecture, and RISC architectures, the rule is they have to support pipelining. So for support of pipelining, the instruction set in ARM architecture are all designed in such a way that they are of uniform size and uniform or fixed length size. So all instructions are of either 32-bit instructions for ARM instruction set, or all instructions are of either 16-bit for thumb instruction set. You do not have variable instruction sizes like 32 bits or 16 bits or 8 bits, like that. Instructions do not vary in sizes. All ARM instructions are 32-bit in size, that is 4 bytes in size. All thumb instructions are 16-bit in size, that is 2 bytes in size. So because of these 32-bit instructions or 16-bit instructions of same length, it helps in what we call pipelining stages to simplify the decoding process quickly. Next, any RISC architecture definitely supports load and store instruction types. Load and store instruction type imply that any operation that has to be done on a data available in a memory, that information, that data must be brought from what we call memory to register, which is called as load operations. And after we operate on the register, then we can update that value back available in the register back into memory location, that is called as store operations. So load operations implies bringing data from memory into register to be operated upon, and store implies that after operating is complete, we can put back the content of the register back into the memory location. So this is called as load store. So in load store instructions in a RISC architecture, one load instruction or one store instruction can normally deal with 1 unit of data. If it is an 8-bit RISC architecture, 1 unit of data here is 8 bits, that is 1 byte. If it is a 16-bit RISC architecture, 1 unit of data is going to be 2 bytes. If it is a 32-bit instruction, 1 unit of data is going to be 4 bytes or 32 bits. So one load instruction can bring in up to a maximum of 32 bits data from memory location into a register. One store instruction can put a 32-bit data from a 32-bit register back into a memory location. So this is normal operations in a RISC architecture. But ARM being not a normal RISC architecture, being an advanced RISC architecture, ARM being not a normal RISC architecture, but rather than that being an advanced RISC architecture, it supports what we call load store multiple instructions. What this implies is in one load instruction, multiple data units, that is multiple 32-bit data units. Multiple 32-bit data units can be brought from multiple memory locations into multiple registers in a single instruction effort. Effort of the programmer is a single instruction. So the programmer writes a single instruction whereby he can copy multiple data units. He can bring in multiple data units from multiple memory locations into multiple registers. Each data unit is 32-bit in size or 4 bytes in size. That is called as load multiple instruction. Store multiple instruction is the opposite case. We can load multiple data, 32-bit data content into multiple memory locations. And each load operation will be taking up to 32 bits of data maximum for loading onto the memory. So ARM architecture, like any other RISC architecture, definitely supports normal load store instructions which deal with one data unit of 32-bit size. But in addition, ARM, being an advanced RISC architecture, also supports load store multiple instructions where multiple data units can be loaded from multiple memory locations into multiple registers, and multiple registers in a register, multiple data present in multiple registers can be loaded into multiple memory locations in a single instruction in both the cases. This type of feature is called as load store multiple instructions. And the benefit of load store multiple instructions in ARM architecture is it maximizes data throughput. Data throughput talks about how many number of data bits or data bytes can be copied from source to destination in a single instruction. So load store instructions in RISC architecture what we call maximize data throughput. All right. Then coming to the last point. Last point means the last point in the slide. So ARM architecture supports conditional execution of instructions. What is this conditional execution of instructions? Let's try to understand. So here, I'm just trying to give an illustration, just a moment. Let us take that this is one instruction. This is another instruction. This is another instruction. Okay, this is an if condition. So I'm trying to explain this using C language format. So this is an instruction. This is an instruction. This is an instruction. Next, suppose if I use else. This is an instruction. This is an instruction. This is an instruction. Okay. So listen up, guys. So assuming that this is a program and all these lines are indicating instructions like that, you can assume. So if we consider a three-stage pipeline. So if we have a three-stage pipeline, this is fetch state, this is decode state. So fetch state, this is decode state, this is execute state. Fetch means fetching instructions from the memory. Decoding means understanding basically what is the machine code which has been fetched and triggering the circuit level operations. Okay, triggering the decode logic for the circuit level operations to be performed for that instruction. Then execution is doing the circuit level operations to complete that operations. I hope you guys are following it. So this is an instruction 1. This is instruction 2. This is instruction 3. This is instruction 4. This is instruction 5. This is instruction 6. This is instruction 7. This is instruction 8, 9, and 10 instruction, 10th instruction. Let us consider this program. So if it is a normal CPU in which it's a RISC architecture and pipelining feature is supported, and conditional execution is not supported in the RISC architecture, then what happens is first instruction comes into fetch state. When the first instruction goes into decode state, simultaneously the second instruction comes into the fetch state. When the first instruction goes into execute state, simultaneously the second instruction goes into the decode state, and simultaneously the third instruction comes into the execute state. So far, I hope it is understood. Okay, so first instruction is being executed, second instruction is being decoded, third instruction is being fetched. Now, if the fourth instruction after the first instruction is executed, then the second instruction comes into the execute state, the third instruction comes into decode state, the fourth instruction comes into the fetch state. So when the fourth instruction comes into the fetch state, then this pipelining proceeds. So at a point of time when the fourth instruction comes into the execute stage, what will be present in the decode state and fetch state? Can you people please tell me? What instruction will be in the decode state and fetch state? Can you people comment? 5 and 6, very good. So when fourth instruction is in the execution stage and fifth instruction comes into the decode state and sixth instruction comes into the fetch state. So if fourth instruction is being executed, if that condition is true or satisfied, then fifth instruction will proceed from decode state to execute state. Sixth instruction will proceed from fetch state to decode state, and seventh instruction comes into fetch state. True or false? True or false? True. Okay, but if fourth instruction's condition does not satisfy, if fourth instruction's condition does not satisfy, then what happens? Fourth instruction is under execute state, fifth is decode state, sixth is fetch state. If fourth instruction executes with success, then fifth instruction comes into decode state, sixth instruction comes into fifth instruction comes into execute state, sixth instruction comes into decode state, and seventh instruction comes into fetch state. But assuming that fourth instruction execution stage condition is false, it fails. So if it fails, what is present in the decode state and fetch state? If it fails, what is present in the decode state and fetch state is wasted, because there are already instructions in the decode state and fetch state. That is, fifth instruction is present in the decode state and sixth instruction is present in the fetch state. So what happens? These two instructions present in the decode state and fetch state have to be flushed out from the pipeline buffer or the pipeline stage, and later eighth instruction must come via the fetch state into the decode state. Okay, first it has to come into the fetch state, then in the next clock cycle it will come into the decode state, and then ninth instruction will come into the fetch state. Then in the next clock cycle, the eighth instruction will come into what we call execute state, and the ninth instruction will come into decode state, and 10th instruction will come into the fetch state. So what are you understanding from this story? Isn't there a lag in the execution? Are you not observing a lag in the execution? There seems to be a lag in the execution, because when condition of the instruction fails, then the pipeline has to be flushed out with those instructions 5 and 6 which cannot execute, and then the instructions 8 and 9 has to be filled in. So flushing out the pipeline and filling in the pipeline with the appropriate instructions based on the condition being failed, this operation will take extra time. Yes or no? This operation will take extra time. So this extra time, we call it as what we call a lag. This extra time, we call it as the lag. We also call it as the latency in terms of execution. The lag or latency in terms of execution. So if this type of lag, now if I'm drawing what we call, if I'm just annotating, now this is a portion of a program. And for this portion of a program, there has appeared a lag or latency in terms of execution. If this lag or latency is repeated several times in many parts of the program, if this lag or latency is repeated several times in many parts of the program, or if this part of the program which I have circled is being uh, repeated iteratively using some loop 1,000 times, then this lag also will appear 1,000 times. Yes or no? This lag also appears 1,000 times. So what happens? Because of this lag appearing 1,000 times, then the throughput of the CPU, the execution throughput, that means the maximum number of instructions that can be executed per unit time, will it be increased or decreased? Very good. So you are understanding the throughput of the CPU is getting decreased here because of the lag. So normal RISC architectures which do not support, I repeat, normal RISC architectures which do not support this conditional execution capability which is present in ARM will have to face this lag, this latency, and this decrease in throughput of execution throughput. But in ARM architecture, we can improve this impact. We can improve on this negative impact. We can improve on this negative impact through conditional execution. What we mean by improve on the negative impact through conditional execution is, okay, even though this instruction condition fails, let this instruction 5 go to the execution state and execute as a NOP, no operation. At the same time, sixth instruction comes into the decode state, and at the same time, eighth instruction comes into what we call fetch state. So when these two instructions pass off in the execution stage as no operations, time is not invested in flushing out those instructions, but rather let those instructions pass off in the pipeline. But when they come to the execution state, they have to execute as NOPs, and the other instructions 8 and 9 will smoothly flow into the pipeline. So what is happening here is we are not investing or wasting time in flushing out the pipeline buffer, but let the other instructions smoothly flow into the pipeline buffer. So since we are not wasting time in flushing out the pipeline buffer, we can minimize the impact of reduction. We can minimize the impact of reduction of execution throughput through this feature called as conditional execution. Is this understood? Please let me know. So we can minimize the impact of the reduction in throughput of a CPU by letting those instructions not be flushed out from the pipeline, but let them pass in the execution stage as NOP operations, no operation instructions. They will not do any operations. They'll not have any significant impact on the registers or flags or anything. They'll just pass off as NOPs, and the other instructions will smoothly flow into the pipeline without time being invested in flushing off first and then bringing in the new instructions into the pipeline. So this type of feature present in the ARM architecture, which prevents the flushing of unnecessary instructions or unrequired instructions and then bringing in the appropriate instructions, that smooth flow is referred to as what we call conditional execution of instructions. So ARM architecture supports this feature that let these instructions pass off and execute as NOPs. This is called as conditional execution. I hope you guys have understood this. Have you people understood this? Okay. Next, continuing with the features. So the ARM core supports 37 32-bit core registers. I repeat, the ARM7 supports 37 in number, 32-bit in size core registers. So just like in 8051, we are having what we call 32-bit, 8-bit registers, which are divided into 4 banks. I repeat, we are having 32-bit, 8-bit registers, which are divided into 4 banks as the core registers of the 8051 architecture. So here the core registers of the ARM architecture are 37 in number, and each register is 32-bit in size. But though there are 37 registers, each 32-bit in size, a programmer at a point of time in a mode of operation, in any of the available modes of operations in the ARM architecture, will not be allowed to access more than 16 registers at a point of time. Though physically the number are 37 registers, we cannot access all the 37 registers in a particular in the mode of operation of a ARM architecture. So there will be some set of registers among the 37 registers which are common to all the various modes of operations supported by the ARM architecture, and there are certain registers which are only accessible in that specific mode but not in the other modes of operations of the ARM architecture. So this is what we mean by, though there are 37 registers, each 32-bit in size, the maximum number of registers that we can access in a mode of operation is restricted by 16 registers per mode of operation, not more than that. In this 16 registers, some registers are common to all modes of operations. Some registers are uniquely accessible in that respective mode, but not in the other modes. Next, the ARM architecture supports what we call, it may support cache, it may not support cache. What is a cache? A cache is a high-speed memory which is placed between the main memory, RAM, and what we call the CPU. So when CPU wants to deal with some kind of data very fast, very expressly, then instead of storing that data temporarily which it wants to deal with in memory, it can prefer to store that information in another high speed memory faster than the normal RAM memory, temporary memory, which is less in speed as compared to the cache type of memory. So this cache memory support, it may not be supported by all ARM cores, it may be supported by few ARM cores, and it may not be supported by some ARM cores. So it all depends on what we call the implementation, whether you have to we have to check the implementation of the core and check whether this core is able to support cache or the core is not able to support cache. We have to check that by looking into the manual pages or data sheets or articles related to the core. Okay. Next, the ARM architecture is not a single core, but it refers to a family of cores. So there is ARM1, there is ARM2, there is ARM3, there is ARM4, there is ARM5, there is ARM6, there is ARM7, there is ARM8, there is ARM9, there is ARM10, there is ARM11, there is ARM Cortex A series, ARM Cortex R series, ARM Cortex M series. So from ARM1 till ARM7, I repeat, from ARM1 till ARM7, it had been one human architecture. ARM1 core till ARM7 cores have been employing one human architecture in terms of designing. One human architecture is called as a memory organization architecture. So a CPU is divided into two architectures based on CPU memory divided in terms of memory organization architecture or in terms of instruction set support architecture. So if it is memory organization architecture, we may have what we call one human architecture, we may have Harvard architecture. If it is instruction set based architecture, then we have what we call CISC architecture, we have RISC architecture. So ARM1 core till ARM7 core supports what we call one human RISC architecture, whereas ARM, what we call 7 onwards, means after that ARM 8, ARM 9 onwards. To be more specific, let's say ARM 9 onwards. So ARM 9 onwards till ARM Cortex series and further onwards. ARM 9 onwards till ARM Cortex series and further onwards are now being designed to support what we call Harvard memory organization architecture. So ARM1 till ARM7 had been von Neumann memory organization architecture, but ARM9 onwards to present ARM Cortex supports Harvard memory organization architecture. So von Neumann RISC architecture, ARM1 till ARM7 is von Neumann RISC architecture, and ARM9 to ARM Cortex series is going to be Harvard RISC architecture. Okay, guys, I hope it's understood. So far? Okay, next. ARM supports 32-bit data bus. So ARM supports 32-bit data bus means the maximum amount of data it can transfer from register to memory or from memory to register. Okay, the maximum amount of memory it can deal with in a instruction is up to 32 bits. So 32-bit data, that is 4 bytes data being transferred over a 32-bit data bus, is a normal thing for ARM architecture. So ARM architecture supports instructions which, in place of transferring 32-bit data, can also transfer 8-bit data from source to destination like that. Or ARM architecture supports instruction which can also transfer 16-bit data from source to destination. So if it supports 8-bit data from source to destination instead of 32-bit data, or it supports 16-bit data transfer in terms of 32-bit data, anyway, it definitely supports 32-bit data transfer. We call these 3 varieties of data transfer instructions supported by ARM architecture as data types in ARM instruction set and assembly language and instruction set. We call this ability of ARM architecture to transfer only 8-bit data instead of 32-bit data, to transfer only 16-bit data in place of 32-bit data, to transfer anyway 16-bit 32-bit data. We say that the ARM architecture supports separate instruction for dealing with transferring 8-bit data, separate instructions for transferring 16-bit data, separate instructions for transferring 32-bit data. So we say that the ARM architecture supports 8-bit or 16-bit or 32-bit data types. Is this understood, please? Next, the ARM7 core that we are discussing supports 7 modes of operations. So when I'm saying ARM7 and you are saying 7 modes of, we are saying 7 modes of operation, please don't be under the guidance that if ARM7 supports 7 modes of operations, ARM8 will support 8 modes of operations, ARM9 will support 9 modes of operations, ARM10 will support 10 modes of operations, ARM11 will support 11 modes of operations. No, do not think in that way. So ARM1 till ARM9, ARM1 till ARM9 support 7 modes of operations. I repeat, ARM1 till ARM9 support 7 modes of operations. ARM1 till ARM9 support 7 modes of operations. ARM10 or ARM11, it supports, I think, around 8 or 9 modes of operations. ARM1 till ARM7 supports 7 modes of operations. ARM11 supports, I think, 8 or 9 modes of operations. ARM Cortex will support a few more modes of operations. So as the complexity of the ARM core and architecture is increasing, maybe the number of modes supported by what we call the ARM architecture also will increase slightly. But as of now, remember, ARM1 till ARM9 supports 7 modes of operations. Since we are learning about ARM7, hence right now ARM7 supports 7 modes of operations. So what are these 7 modes of operations? These are hardware modes. I mean, these are modes which will decide the accessibility of the 37 registers that have been mentioned a few minutes back. So ARM core supports 37 32-bit core registers. So the the protection for these 32-bit 37 registers is decided by using these 7 modes of operations. So among the 7 modes of operations, in all modes of operations, there will be some registers among the 37 registers which will be common to all modes of operations, but there will also be few registers which are accessible only in specific modes of operations, but not in other modes of operations. So these modes of operations of ARM architecture are divided into two parts. One is called as the privileged modes of operations. The other one is called as non-privileged modes of operations. So please have a reading of this. I will explain. Okay, guys. So the privileged mode of operation says that it allows full read-write access to a register called as CPSR register. So we have a kind of register in ARM architecture, that is the ARM7 architecture. We have a register called as CPSR register, which stands for current program status register. This current program status register is also called as the flag register of the ARM architecture. So the processor mode determines which registers are active and access rights to the CPSR register. So out of the 37 registers, which registers can be accessed in which modes of operations only, and registers which are common to all modes of operations, and the CPSR register flags are there. So CPSR register is a 32-bit register, and 32-bit register will be having certain flags, flag bits. So which flag bits can be modifiable, that is readable, you can access it completely or incompletely. That will be decided by what we call the modes of operations. So if I go for a privileged mode of operations, we can access all the 32 bits of the CPSR flag register bits. Okay, we can access them for read or write access. Whereas if you go for a non-privileged mode, it says that only read access is allowed to the control field in the CPSR. So actually the CPSR, which is a 32-bit register, is divided into 4 parts. Bit number 0 to bit number 7 is one part. Bit number 8 to bit number 15 is another part. Bit number 16 to bit number 23 is another part. Bit number 24 to 31 is another part. Means these 4 parts are referring to as 4 fields. We have the control field, we have the extension field, we have the status field, and we have the flags field. I repeat, bit number 0 to bit 7 is called as the control field. Bit number 8 to bit number 15 is called as the extension field. Bit number 16 to bit number 23 is called as the status field. Bit number 24 to bit number 31 is called as the flags field. So in the non-privileged mode of operation, what it says that it allows only read access to the control field. So the control field, we can go for read operation only, but we cannot go for a write operations. But it allows read write access to the remaining other fields. In this case, in our case, that is ARM7, we should not bother about the extension field because that field features are not present in the ARM7 core. We should not bother about status field because that field features are not available in the ARM7 core. So we should only bother about control field and flags field. So non-privileged mode allows only read access to the control field in the CPSR, but allows read-write access to the condition fields. That is bit number 24 to bit number 31. It allows read-write operations completely. And bit number 0 to 7, it only allows read access to the CPSR. Is this understood, please? Hello, is this understood? Any questions still here? Flag CPSR flag diagram I will give later. It will come anyway. It will come when I start discussion of the registers. Then that information will come anyway. No problem. Okay, let's proceed. So the 7 modes of operations in which it is broadly divided into privileged mode and non-privileged mode. So we have 6 privileged modes, namely called as abort mode, fast interrupt request mode, supervisor mode, and undefined mode. These different modes of operations, abort, fast interrupt request, supervisor mode, system mode, and abort mode, make up 6 privileged modes of operations, and 1 unprivileged or non-privileged mode of operation is called as user mode of operations. So I will be briefly describing about these modes of operations shortly. So to begin with, starting with the abort mode. Now, abort mode is a kind of mode which is having 2 types. One is called as the prefetch abort. The other one is called as data abort. So prefetch abort is a kind of mode in which the CPU will enter whenever it wants to fetch an instruction from the code section, but it is unable to access the code section. So if the CPU, that is the ARM7 core, intends to fetch an instruction from the code section, but maybe that code section is physically not available, though the address number is there in the instruction, but probably that physically that memory location is not available, and since it is not available, there is no content in that memory location. So when the CPU tries to access a region of ROM memory, read-only memory for an instruction which is not accessible, that part of the memory or that part of in that instruction is not available in that memory, or that memory location itself is not accessible or is not physically available, then this gives rise to a type of interrupt. This gives rise to a type of interrupt that is called as abort interrupt, prefetch abort interrupt. When this attempt to access a region of memory is not possible, it gives rise to what we call a prefetch abort interrupt. And because of the prefetch abort interrupt, the CPU switches from its normal usual mode of operation, that is called as user mode of operation, to enter into what we call abort mode of operation. The default mode of operation of a CPU, ARM7 CPU, is going to be supervisor mode. Whenever it is powered up upon default, it will be in supervisor mode. While the CPU is in supervisor mode, we as a programmer should configure the stack pointers for all the 7 modes of operations and then switch the control of the program counter switch the control of the program counter into the programming part or application part, which will start executing the main logic. And when the main logic is executing, if an interrupt is raised, because CPU is unable to fetch an instruction from the code section, then the control of the CPU enters by coming out of user mode of operation and entering into what we call abort mode of operation. Is this understood? Please let me know. Is this understood? Please let me know. Did you understand what is abort mode? So another example of abort mode can be explained like this. Let us say you have encountered something like a segmentation fault. Let us say that you have encountered something like a segmentation fault in which the CPU is trying to access a region of memory where it is not allowed to access that region of memory. If a CPU is wanting to access a region of memory, but that memory region is not physically available, or it is not allowed to be accessed, then that gives rise to what we call a segmentation fault in a desktop computer running a Linux operating system. But here I'm talking in terms of core, that a CPU wants to access a region of memory which is physically not present. That memory address is there in the instruction, but the memory location is physically not present. So it gives rise to what we call an abort interrupt. Then we have data abort. So prefetch abort is trying to fetch from the code section but unavailable. Data abort is trying to fetch from a data section or RAM section but not able to access that RAM location because it is physically not present. That is giving rise to what we call data abort. Okay guys, hope you have understood data abort and prefetch abort, which are the two types of modes of operations whenever the CPU experiences CPU or data abort. The next mode of operation is called as the fast interrupt request mode. Fast interrupt request mode implies that when the ARM core is going to entertain lots of peripheral devices such as UART, such as I2C, such as SPI, such as external interrupts, such as DMA controller, such as timers, counters, timers, and any other kind of peripherals or devices. So all these kinds of peripherals or devices may be entertained with two levels of interrupt management. One is from the ARM core point of view. The two levels of interrupt management are namely fast interrupt request interrupt level and interrupt request interrupt level. So the difference between them is the fast interrupt request interrupt level is having a higher priority than the interrupt request interrupt level. Means if two interrupts come into the ARM core at the same time, one coming through fast interrupt request interrupt level and other one is coming through interrupt request interrupt level, then first priority to be executed, first interrupt to be executed will be given preference to fast interrupt request interrupt priority level compared to interrupt request interrupt priority level. So whenever interrupt occurred due to fast interrupt request interrupt priority level, the control of the CPU switches from the user mode of operation to FIQ mode of operation. If interrupt occurred due to normal interrupt level request, CPU switches from normal interrupt request from user mode to normal interrupt request level mode. If an instruction being fetched by the ARM core is an instruction called as SWI instruction, that is called as software interrupt instruction. So if the ARM core fetches an instruction of type SWI, which stands for software interrupt instruction, then the CPU enters from user mode of operation to what we call the supervisor mode of operation. The supervisor mode of operation is the default mode of operation of the ARM core. So when ARM core is powered up, by default, it will be in supervisor mode where system level initializations will be done. After system level initializations are being done, the CPU will be made to switch from supervisor mode of operation to user mode of operation, where user can can execute his applications in the user mode, gaming applications or any program development related applications. He will be doing that in the user mode of operations. Only when the necessity of uh, the CPU comes, it will go from user level mode of operations to supervisor level mode of operations through a type of instruction type called as SWI instruction. Next, you have system mode of operation. System mode is referred to as the privileged mode of the user mode of operation. So in user mode of operation, there are some restrictions for accessing the flag registers. In system mode of operation, you do not have the restrictions that you are having to access flag register. So what are the restrictions of the flag register in non-privileged mode? That restrictions will no longer be available or valid in privileged mode of operations. Okay, guys. Okay, guys. Then coming to what we call the uh, undefined mode of operations. So the ARM architecture is not a single core, but it is a family of processor cores. So there may be some instruction present in a core which may not be present in another core, for example. So all instructions of the ARM core, there may be instructions which are commonly available in all cores, but there may be some typical instructions which is present in one core but is not present in the other core. So this will happen usually when you go from a lower core to a higher core. Higher core will support additional instructions which is not present in the lower core, but it will support all the instructions of the lower core, let us say. So whenever you're trying to execute a program written on a higher core, mistakenly on a lower core, if you try to execute a program written on a higher core, written for a higher core, mistakenly on a lower core, when the lower core encounters an instruction during its fetch state and sees that this is particular instruction is not supported by the ARM core, which is executing this instruction, then it will enter into a mode of operation called as undefined mode, indicating that I have encountered during the execution of an instruction which is not supported by the present core, which is executing this instruction. So such kind of error message is indicated by the ARM processor core switching from what we call the mode of operation, let us say user mode, to what we call undefined mode of operation. Undefined mode of operation can also be used for what we call math co-processing instructions. So if a ARM being a main processor, if it is attached to another helping processor or auxiliary processor called as co-processor. So when ARM processor fetches an instruction which belongs to the co-processor but not the ARM processor. So it fetches an instruction from the memory and tries to execute that instruction, but that instruction is not supported by the ARM core, but it is supported by the co-processor instruction. Then the ARM core enters into a mode of operation called as undefined mode. So when it enters into undefined mode, it may imply that the control to handle the execution of this instruction which it doesn't support is going to be entrusted or directed to another CPU which can understand that instruction and execute that instruction, generate its output or collect any response or feedback. This operation will take place in what we call the undefined mode of operation. Is this understood, everybody? Hello, people. Okay, so all of you please have a reading. The non-privileged mode or user mode is the normal mode of operation which the CPU mostly will be in. Default mode of operation of CPU is supervisor mode. From supervisor mode, we switch to user mode, and we will be in the user mode. Whenever these interrupts are raised, they will switch from user mode to their respective modes based on the type of interrupts occurring. So everybody please read the slide over here. Okay, guys. Next, look at the next slide. Okay, people, have you finished the reading? Okay, let me come back to the modes of operations once again and try to explain these modes of operations in a different way. So again, I come back to the modes of operations where we are having what we call the 6 privilege modes: abort mode, fast interrupt request mode, supervisor mode, system mode, undefined mode, and then the user mode. Now let us talk about our mobile phone. Okay, let's talk about the cell phone in our hand, your smartphone right now. Because that's what is mostly being used. Let's try to compare the smartphone which uses an ARM core with respect to these modes of operations. So whenever you purchase a smartphone, it will have already some inbuilt programs which comes what we call preloaded inside the ROM of the smartphone. True or false? It will also already have an inbuilt program that is called as an operating system, which comes preloaded into the ROM of the ARM, ROM of the mobile phone. True or false? So when you switch on the mobile phone, what happens is the moment you switch on the mobile phone will be in, let us say, supervisor mode. Supervisor mode is considered as the most what we call it's considered as the highest privilege level mode, you can say. All these are, we are having 6 privilege levels, so the default mode of operation is the supervisor mode. So the cell phone will be in the supervisor mode as it is powered up and booting. So during this supervisor mode, as it is powered or booting, it will be executing all the core functions of the operating system in order to initialize the mobile phone. that is happening in the supervisor mode. So while it is initializing all the core operations related to the cell phone in the supervisor mode, no sort of inputs or no sort of inputs from the user will be always acceptable. Like if you connect an audio jack, or if you try to uh, get a call or something like that during the boot process, nothing of that sort of thing will be affecting the mobile phone. So the supervisor mode is a mode which is the most privileged level mode, and it is the mode which will be executing the operating system of your cell phone. And while the operating system is booting, it will be in the supervisor mode. So as it is booting, it will initialize the mobile phone with the core operations, and after that it will bring up the what we call GUI interface. And when it brings up the GUI interface, on the GUI interface, you will be seeing what we call icons on the screen. And these icons on the screen through the GUI interface are indicating the default apps which come inbuilt with the operating system. Okay, so these are the default apps. Now, you may not have a privilege to uninstall these default apps from the operating system uh, environment. Is it true or false? You may not have privilege to uninstall these default apps in the operating system environment. True or false? Please answer the question. You may not have privilege to uninstall or delete these default apps from the environment of the operating system. Why? Because these default apps are running and available in the privileged mode, which is not accessible to the normal user in user mode. So this is what I mean by supervisor mode, which is called as the most privileged level mode. Is this understood up till here? Please let me know. Is it understood here up till here? Please let me know. So when you click on some kind of app in order to upgrade it, whenever you click on some app, let us say you want to upgrade the WhatsApp, or you want to upgrade any other app which is there inside your mobile phone environment. So the moment you click on it, the clicking of it will make the CPU switch from user mode of operation, because when an interface is given to you, that is the screen with the icons, you are in the user mode of operation. So when you press on that button or you click on that icon, it will switch from user mode to what we call it will switch from user mode to what we call the supervisor mode. And while it goes into the supervisor mode, it will help you to what we call upgrade the app version. It will help you to upgrade the app version of the uh, apps which come along with the operating system. So all this happening from user mode to supervisor mode. When you click on it, it switches to supervisor mode and helps you to upgrade the app. And then after upgrading the app, then it will again what we call run the app in the user mode. Once the app is upgraded and you click on it, it will help you run the app in the user mode of operation. But upgrading the app will be done in the supervisor mode of operation. Now, when you go to Play Store and you try to install a new app which is not pre-installed with the kernel, this type of operation will be taking place in what we call the system mode. So system mode is that mode which is like user mode, but it has privileges. So new apps which are going to be installed inside the cell phone from the Play Store will be installed in the system mode of operation. Okay, they will be installed in the system mode of operation, and user will have privilege to again uninstall them as well as to upgrade them. He can uninstall those apps. He can also upgrade those apps, but those apps are going to be available. They are going to be upgraded. They are going to be uninstalled. The instruction for uninstalling that all will be available through what we call system mode. The apps will be running in user mode, but if I want to upgrade that app or I want to uninstall that app, it will be possible through what we call system mode. So system mode is a privileged level of user mode. That is about another way of trying to explain what is supervisor mode and system mode in another way. Is it understood, please? Everybody? So I've tried to explain supervisor mode and system mode in a slightly different way using your cell phone. Fast interrupt request mode and interrupt request mode are nothing but interrupts which are handled by the ARM core. So if I connect an audio jack is a sort of an interrupt. If I try to, if a mobile phone, I mean, if a, what do you say? If I'm playing a music and suddenly a mobile phone comes, a call comes, sorry, if a call comes, that is a sort of interrupt. So whenever interrupts are being given to an ARM architecture from devices like UART, I2C, SPI, external interrupts, analog to digital converter interrupts, digital to analog converter interrupts, timer based interrupts, all these interrupts may be entertained either in a fast manner, hence called as fast interrupt request, or it may be handled in a normal manner called as interrupt request. So fast interrupt request, the name is because it entertains that interrupt in a fast way by reducing the switching time from user mode to interrupt service routine. When it is reducing the switching time from user mode to interrupt service routine in a short time, we call it as fast interrupt request because the context saving time in the case of fast interrupt request is less as compared to the context saving time that will be invested for interrupt request. Less time will be invested in context saving for fast interrupt request. Hence, it responds to the interrupt more faster as compared to the time invested in context saving for interrupt request. So, interrupt request will take a little bit more time in order to respond to the interrupt request. Hence, that is the difference between fast interrupt request and interrupt request. Abort mode I already explained. Inability to access a memory location may give rise to segmentation fault, which will give rise to abort interrupt. Experiencing a type of instruction which is not supported by the core when it is fetching and trying to execute, decode and execute, that is called as an undefined mode. So that brings us to what we call the briefing or discussion about the 7 modes of operations. So with this, we'll stop here with the ARM architecture, take a break of 20 minutes and meet at 12 o'clock and continue with I2C protocol. Okay, guys? Okay, people? Right. So let's meet at 12 o'clock again.